This is LB 273 Formal Lab 2 by Sullivan, Aubrey, and Ian.
Through this experiment, we are hoping to answer how mass affects the terminal velocity and acceleration of an object as it falls through the air. We are also hoping to answer how the mass affects the drag force and how the change in drag force amongst three different masses impacts the terminal velocity. Our overall motivation is to determine how mass affects terminal velocity.
Our findings from our results were the larger the drag force, the faster the coffee filter hits the ground. The larger the mass, the faster the coffee filter hits the ground. The more coffee filters you add, the faster the terminal velocity is, which means the faster the coffee filters hit the ground. The larger the terminal velocity, the larger the uncertainty in terminal velocity, and the larger the terminal velocity, the larger the coefficient of drag and drag force.
Before we begin the experiment, it is important to recognize that the terminal velocity is a constant velocity that an object reaches when the drag force is equal in magnitude to the gravitational force, preventing further acceleration. The drag force is the resistance that the coffee filters or another object experience as they travel through a fluid such as air. And the coefficient of drag is dependent on the object, but it quantifies how much an object resists motion through a fluid.
Here we just laid out our experimental design where we show the schematic setup and our system schema.
These are the pie charts for this scenario. Since the circles are represented as the same size throughout the scenario, that means energy is conserved. And as you can see at the start, it starts at 100% potential energy, and when it's about to hit the ground, it's at 100% kinetic energy.
These are the free body force diagrams for this scenario. Before terminal velocity is reached, the force of gravity on the coffee filter is greater than the force of air resistance on the coffee filter. However, after it reaches its terminal velocity, these forces are equal. Here we have the position, velocity, and our acceleration graphs for this scenario. We are going to use the slope of the position graph to find the terminal velocity by adding a linear curve fit and fitting it to the portion of the graph where the slope of the position graph is linear and no longer curving. This gives us an accurate reading of the terminal velocity with a small uncertainty. This applies for the graphs of all three trials. This slide shows the graphs of one coffee filter. Here we have
These are the three motion graphs for the stack of 5 coffee filters.
These are the three motion graphs for the stack of 10 coffee filters. These are the example calculations for our experiment where we calculated terminal velocity / coefficient of drag and then drag with those examples here on the right. So the time that the coffee filter stack reached terminal velocity was determined by looking just out when the acceleration reached 0 on the graph, and then terminal velocity was found on previous slides by the slope of the position graph.
This slide shows our data and calculations. The terminal velocity and uncertainty of terminal velocity for all three trials were found on the respective tracker graphs, and the coefficient of drag and drag force were found using the equations shown on the previous slide.
These are just our results for the 1 coffee filter stack, 5 coffee filters.
For our data analysis, we determined that terminal velocity increased as more coffee filters were stacked, indicating that the heavier stacks fell faster until the magnitude of the drag force is even with the magnitude of the gravity force. Small experimental uncertainties indicate small measurement inconsistencies, and the uncertainty in the terminal velocity measurements increased with the number of coffee filters, indicating that the heavier stacks, which fell faster, were more difficult to measure precisely. This leads to slight variation in the drag values as well. This uncertainty may also come from the coffee filters twisting throughout the air. This was minimized by dropping them straight down.
To wrap it up, these are our predictions and reflections. So for our predictions, we predicted as mass increased, terminal velocity would also increase. Heavier stacks would experience a greater gravitational force requiring a higher velocity for drag to balance it, and that lighter stacks will reach terminal velocity faster because drag weight equals weight sooner. And then for our reflection, the terminal velocity rose with mass. Heavier stacks needed greater speed for drag force to balance out weight, and as expected, drag force did increase with mass. Slight variation due to confounding variables like air current or human error, but overall the trend matches our predictions.